Welcome back, everyone. Let's dive into another session together. So today we're going to be looking at reactive programming. Yeah, a really popular topic right now, especially for Java developers. Okay, so let's get into it. What is reactive programming? Reactive programming is a declarative programming paradigm concerned with data streams and the propagation of change. Basically focuses on reacting to data changes and events. What parts of that definition tend to confuse people the most? I think one of the harder things to wrap your head around is this idea of declarative programming, because it's pretty different from the imperative style that so many of us are used to. So instead of telling the computer exactly what to do step by step, you're sort of ascribing the outcome that you want, and then letting the system figure out how to get there. Oh, so you're not like micromanaging every little detail. It's more like you're the architect laying out the blueprint. A good analogy might be SQL queries. So you tell the database what data you want to get back, but you don't tell it how to actually go and find that data. That all happens behind the scenes. And then there's this whole idea of data streams. How is this different from how data is usually handled in like a normal Java web application? Well, in most web applications, you have this request-response model. So a request comes in, the server processes it, and then sends back a response. And it's all very linear. But with reactive programming, you're thinking about data as this constant flow. It's like a stream of events that your app needs to react to instead of these like discrete chunks of data. So it's much more dynamic, kind of like how a user interface reacts to clicks and inputs. In the definition, propagation of change means that when data in a reactive stream is modified, any dependent parts of the system are automatically updated. This allows for efficient and consistent data flow without explicit manual handling of updates. Another analogy for reactive programming would be to spreadsheets, something about declaring dependencies and letting the system handle updates. Think about how you set up formulas in a spreadsheet. You might have a cell that adds up the values in two other cells. If you change the value in one of those input cells, the sum automatically updates. That's kind of like what reactive programming is all about. You define these relationships between different parts of your system, and then you just let the system propagate those changes for you. So it's like a chain reaction, but for data. We've briefly explored reactive programming and hope it has clarified some concepts around it. Moving forward, we'll explore its four core principles: responsiveness, resilience, elasticity, and message-driven. Let's take a closer look at each. Responsiveness. The system must respond quickly to user input and data changes, providing fast feedback to maintain a smooth user experience. It ensures low latency and prevents the system from becoming unresponsive during high load. Resilience. A resilient system can continue operating even when parts of it fail, recovering gracefully without affecting the overall service. It isolates failures to prevent them from cascading and impacting other components. Elasticity. Elasticity allows the system to automatically scale up or down based on demand, handling fluctuating workloads efficiently. It ensures that resources are allocated dynamically, optimizing performance and resource usage. Message-driven. Data is communicated asynchronously through messages, enabling components to operate independently and in parallel. This decouples system parts, improving flexibility and allowing better performance through parallel processing. Let's jump into why might a server-side Java developer be interested in reactive programming? I gotta be honest, there's a part of you might still be wondering, why should a server-side Java developer, someone who's not like building user interfaces, really care about reactive programming? Where does it fit into backend development? It goes into some of the limitations of these traditional web backends, especially this idea of the thread per request model, which can really become a bottleneck when your app is under heavy load. Yeah, they really show how all of those threads can get bogged down waiting for stuff, like waiting for responses from the database. It's like they're clogging up the whole system. It's like a traffic jam inside your server. Every request is holding onto a thread, even if it's just sitting there waiting. And as you get more and more requests, the whole system just grinds to a halt. So how does reactive programming solve this problem? Is it like magically make those database calls faster? Not really. It's not about making individual operations faster. It's about fundamentally changing how you deal with concurrency and how you manage resources. So instead of using one thread for each request, reactive programming lets you process those requests asynchronously and in a non-blocking way. So imagine you're at a restaurant, and there's a waiter. In a traditional system, the waiter takes your order, goes to the kitchen, waits for your food, and then brings it to your table. But while they're waiting, they can't serve anyone else, right? So it's very one-to-one, very synchronous. But in a reactive system, the waiter takes your order, and then they immediately move on to help other customers. When your food is ready, someone from the kitchen brings it out. The waiter isn't tied to just one request, so they're free to handle a bunch of orders at the same time. Even if some of those orders involve waiting around, it really shows how reactive programming can make things more efficient. That's just one of the benefits. There are a whole bunch of other advantages, like being able to write code that's easier to read and maintain thanks to ideas from functional programming. Let's see reactive programming libraries in Java now. Java offers several powerful libraries to implement reactive programming, each tailored for different needs. Let's explore the key ones: Project Reactor, RxJava, AkaStreams, Vertex, Mutiny. Project Reactor. This is the library we'll focus on today, since it powers Spring Web Flux. It provides two critical abstractions, Mono and Flux, which we'll discuss shortly. It adheres to the reactive stream specification, meaning it works seamlessly with other reactive tools. A Java implementation of ReactiveX, another popular reactive programming framework. Similar to Project Reactor, but offers types like observable, single, and flowable. AkaStreams, great for building distributed and highly concurrent systems. Uses a different abstraction layer based on actors, but it's still reactive. A toolkit for building reactive applications with event-driven APIs. It's especially good for microservices. A newer library focused on simplicity. Works well with frameworks like Quarkus for cloud-native development. All these libraries give us tools to handle asynchronous streams, compose transformations, and manage backpressure effectively. Among them, Project Reactor is particularly important for developers working in the Spring ecosystem. Now let's shift focus to Project Reactor, which provides the foundation for reactive programming in Spring Web Flux. Two fundamental concepts here are Mono and Flux. Let's break them down. Mono. A mono represents a publisher that emits either one item or no items. Think of it as a container for a single value or an empty response. You can use Mono for operations like retrieving a single record from a database or signaling that an operation has completed successfully. For example, look at this code snippet for Mono. When you subscribe to this Mono, it will emit the value "Hello Mono" and then complete. If no value is available, the Mono will simply complete without emitting anything. Flux. A Flux, on the other hand, represents a publisher that can emit 0 to n items. Use it for scenarios where you're dealing with streams of data, such as retrieving a list of objects from a database or streaming events from a sensor. For example, look at this code snippet for Flux. When you subscribe to this Flux, it will emit the numbers 1 through 5 sequentially. Once all items are emitted, it will complete. Let's take a moment to clarify some key terms that often come up when we talk about reactive programming. These concepts can sometimes seem interchangeable or confusing, so it's important to understand their distinctions. Are reactive programming and asynchronous programming the same? Not exactly. While many people use these terms interchangeably because both deal with events occurring out of order, they focus on different things. Asynchronous programming is about managing tasks that don't need to run sequentially. The goal is efficiency, avoiding idle time by letting your code move on to other operations while long-running tasks like API calls or file reads complete in the background. Reactive programming, on the other hand, is all about data flow, how changes to data ripple through your system in real time. It's less about managing tasks and more about designing systems where components react dynamically to data updates. How does functional programming relate to reactive programming? Here's a good way to think about it. Reactive programming is like managing a data stream, and functional programming gives you the tools to shape and control that stream. Functional programming provides concise, declarative ways to manipulate and transform data, like using filters, maps, and reduces. Imagine your data flowing through a network of specialized pipes and filters. Functional programming helps you construct those pipes with clarity and precision, making reactive systems cleaner and more efficient. What is back pressure? Back pressure is a crucial concept in reactive programming. It handles situations where a data producer is faster than the consumer can process. Without back pressure, this mismatch could lead to memory overflow or a system crash. Back pressure acts as a stabilizer, allowing the consumer to signal the producer to slow down or buffer data until it's ready. This ensures the system remains responsive and efficient, even under heavy loads. What is a circuit breaker? The circuit breaker pattern is another important tool, especially for building resilient systems. Think of it as a safety switch. If one part of your system starts failing, say a service takes too long to respond, the circuit breaker steps in and stops further requests to that service. This prevents the failure from cascading to other parts of your system. After a cooldown period, the circuit breaker can retry the service or redirect to a fallback mechanism, ensuring your system continues to function smoothly. Understanding these terms is essential for mastering reactive programming and building systems that are efficient, resilient, and scalable. Let's keep exploring. As we wrap up, it's clear that this paradigm is more than just a trend. It's a necessary evolution for building responsive, resilient, and scalable systems in an increasingly connected world. The demand for systems that can handle asynchronous data streams, adapt to fluctuating workloads, and recover gracefully from failures is only growing. Reactive programming positions us to meet these demands head-on, delivering experiences that are both seamless and efficient. Looking to the future, reactive programming will continue to shape how we approach modern software design. With the rise of cloud-native applications, IoT, and real-time data processing, the principles of responsiveness, resilience, elasticity, and message-driven architectures will become even more critical. Well, that's a great place to wrap up. I hope you learned something new today. Until next time, happy coding, everyone.